Now with our final speaker, we're doing a bit of a full circle, going back to data, following on from Rui's presentation at the start. Markus Bradke is going to talk about an implementation they've done of that GFZ.
All right.
Thank you.
Thank you, Ryan. Yeah, following on from the discussion that Rui started earlier this morning, I would like to give you an example of an actual implementation of a GNSS data lakehouse. So first of all, what is the motivation to change anything from the current status of a POSIX-like repository that we have at the moment? First motivation is the actual data volume. So you can see a plot here for the station Potsdam that was installed in 1994. And yeah, back in the days, we had 30 satellites, only one constellation. We only tracked in 30 seconds with 30-second sampling interval. And you can see over the time how we added constellations, frequencies, tracking modes, changed our sampling rate from 30 seconds to 1 Hertz. And if we multiply that by the amount of stations that we are currently having in the IGS network or that are processed at Nevada, for example, you can see that the data volume is it's getting a bit of a stress point for the data centers. So that is motivation number one. Motivation number two, already something mentioned by Rui this morning, is the RHINEX format itself. It is optimized for file exchange, but it's not optimized for cloud scale analytics. So RHINEX is file oriented. You can use it on a POSIX file system. And we have a mandate by our organization now to move data into an object store, which has a completely different architectural model behind. That's one point. The other one is that we have a small files problem. So we have data sets that contain millions of small files, and each file is basically a separate S3 request, which then cause basically a high cost and a high latency. And we have also inefficient access patterns for our analytics. So RHINEX is text-based and not a columnar format. So we have no ways of indexing or filtering at a source. So we always have to perform a full file scan to get maybe a minimum of information that we're actually interested in out of the data. And we also have poor scalability for many files. So if we are on an object store, just the metadata overhead of putting all these small files in a bucket makes it really slow at the end. And one of the major problems that we see with RHINEX is that we have no flexible data access. So we cannot simply query a subset of data. We always have to download the full file and basically extract what we need. Yeah, and the third motivation that we had is the limitation in our traditional data center. So we have a monolithic pipeline where we have tight coupling between ingestion, processing, and the storage, which makes it hard to scale and hard to evolve. And we also, with RHINEX, we have an operational complexity. So we always have to perform sampling and merge operations on the file, which makes it really complicated at the end. And we are also very, let's say, inflexible for analytical demands. So that's what Rolf already mentioned, just adding a 24-hour second. You have to merge basically two files, and that's not really a good approach. So we want to move and use or create a modern GNSS platform. So we first looked at the functional and non-functional requirements that we put on that platform. Functional ones are, we want to be able to ingest our data in a scalable fashion. We want to allow access to the data for multi-engines. and we want to efficiently query our data. Yeah, I already said we have to move into an object store, so the format has to be cloud optimized and cost efficient. We want to use open formats, and we also want to be vendor neutral. All right, that all led us to the design of a data lakehouse. Now you might ask what a data lakehouse actually is. And at the end, it's an architecture that combines the best of both worlds that we currently have. So one is a data lake, which is basically a scalable low-cost object storage such as Amazon S3, Google Cloud storage, or Azure Blob, and a data warehouse. And a data warehouse is basically features structured tables, asset transaction, schema enforcement, and fast SQL analytics. All right, other features that a data lakehouse have are asset transactions, so we can concurrently and safely write into the lakehouse. We have a schema evolution, so basically you can think of the Rhinix data as a columnar table, and if we have an update on the Rhinix format as it is now, we can basically update the table columns without breaking the history. We also need partition evolution. So to efficiently query the data, you need to partition the table by certain fields. So partition evolution, you can update the partitioning schema without rewriting the whole table. We also have hidden partitioning and time travel features that are relevant here. All right, now I would like to show you a simplified version of our system design that we came up with. So you can see at the top, it's basically observation data pouring in from remote locations. It doesn't matter if they come from SFTP, HTTPS, S3, we can handle them. Then we have a Kafka message broker in the middle, where we actually basically write to the Kafka broker, make or write a message to a topic, and the other microservices then can subscribe to these topics and can perform operations basically on a millisecond base. The major point that we have here is an ETL pipeline. So we actually extract the raw observations from Rhinix. We transform them to Apache Parquet, and we can then load that Apache Parquet format into Apache Iceberg, which is our data lakehouse. As a side container, we have a PostgreSQL database that has information about the station metadata, as you know from the IGS site logs. We build a data access API so that you can access the raw observations directly, the station metadata, and also get the data availability. And that all then can be used in actual dashboards. You can use it for notification systems or simply access the data in a direct way. To the storage layer. So as said, we are using Apache Iceberg. We have CephFS as our S3 storage that we use at GFZ. The data is written in Parquet files with a table-specific partitioning. So we partition by station and by day at the moment. And on the right side, you can actually see a little bit how Iceberg works. It's a simplified version. So Iceberg is basically a smart metadata layer that tells the engine exactly what files to read and which to ignore. And a query actually works in a way that the engine asks the catalog, where's the table? The catalog returns a pointer to the metadata, And the metadata then tells the engine which files to read, which to skip, and then the engine can read the relevant data files that are relevant for that query. Just a quick introduction to our observation model. It supports rapid spatiotemporal queries with orthogonal slicing. So we basically have the 4 dimensions of station, epoch, satellite, and signal. And we then store the actual observations, phase code, signal to noise, Doppler, loss of log information on a row level. All right, we also built a data access API, which is then connecting to the Apache Iceberg PostgreSQL metadata catalog. We support response types for Apache Arrow, Apache Parquet, and currently Rhinix 3 and Rhinix 4. And we can query the data by station, time range, sampling rate, constellation or satellites, signals, and we could also just say, give me the properties of phase and code if you're interested in that. Service is not publicly available yet, but I just wanted to have a quick example of how a query could look like. And the last point that I want to mention is we have a lot of microservices running in the background. So to ensure that they are all running smoothly and not causing any trouble, you need an observability layer. So we use Prometheus for continuous logging of the service metrics, Alloy and Loki for the service logs, and we use Grafana for the visualization and for the alerting system, just to mention. We performed some benchmark tests on our developer notebook, which is an Apple M4 Pro with 12 CPU and 32 gig of RAM. And we performed benchmark tests for first the ingestion. There we used PyIceberg. We used our GFZ archive to test the processing. So we basically have 50 stations, all tracking in 1 Hertz, all in Rhinix version 3. And we have 1 year of multi-GNSS data. We set up 10 parallel workers, and we basically could ingest our data with a median total time of about 1 second. So if we would scale it up or do the maths here, we could ingest a whole year of GFZ data in 3 days. So, all right. The other benchmark that we performed was a data access benchmark. So we're using Fast API for our API and Trino as the query engine. And our benchmark test was here basically how the IGS analysis centers currently use the data. So we have 120 parallel requests requesting daily 30-second observation data, which is basically used in a rapid or on an ultra. And we have Apache Arrow as the response type. So the median request duration was between 9 and 11 seconds. And the total wall time, so the time from the for asking for 120 stations and getting them all back, was between 5 and 6 minutes. This is comparable to when you go to CDDAS, download the data, perform your dHatanaka, decompress the file, use GFZ RNX, for instance, to get the data out that you need, which is round about the same time. All right, conclusions. GNSS archives are becoming analytical data sets. So the Lakehouse architecture enables reproducible cloud-optimized GNSS analytics. The object storage simplifies the operations at scale. We have a portable deployment procedure with individual microservices. We can scale the data for the ingestion and also for the access. And we have a real-time monitoring with commonly used components. And just to wrap up lessons that we learned, because it's all new, it's all a bit different. The problem that we saw is that small files become the dominant scalability problem. So if you write a lot of small files, you also write a lot of metadata that needs to be accessed. So we actually need to perform some aggressive compactions into the underlying Apache Parquet format. We also need to see that the partitioning strategy that we choose is critical. So if we are to cores, that will cause large scans. On the iceberg tables, if we're to find, we have exploding partition counts, which also doesn't help with the querying. The maintenance is essential to keep the data lake healthy. So you can't just think of rewriting data into iceberg and everything is fine. No, you also have to make sure that your data lake actually stays healthy and that the query performance doesn't drop because of the small files issue that we also have here. All right, that's all from my side. Thanks.